So let's get started. So exam one, we're going to go through it a little bit quick because a lot of these questions should be easier for you at this point. But number one, so 5.3 times 10 to negative 2 is the same as what? So if we write the scientific notation out, it's 0.053. We should use a less thickness on this one. So it looks like 0.053. That's the same as 5.3%. So that is C. So 5.3 out of 100 is 5.3%. That's the same thing as this scientific notation. All right, next. So the image below represents particulate view of a sample of matter. Which of the following best describes it? So you see that it is a compound, because if you look at it, you have a white ball in the middle and then two of these darker shaded balls on the outside. So there's one atom that's different in the middle and then two other different elements around it. So it is a pure compound. It's not a pure element because there is differentiation between them, but each of these molecules are the same. So it's a pure compound. And it's not a mixture because there's no all these particulates are the same type. Next, this one, a lot of you were troubled with the wording. It was kind of tough to understand, but I'll break it down. So the atoms in a molecule move around 1 kilometer per second. Breaking a chemical bond involves atomic motion of around 1 angstrom. So an angstrom is smaller than a nanometer. So it's really tiny distance that is usually represented the distance between atoms in bonds, right? So 10 to negative 10 meters. Therefore, it follows that the time scale of atomic motion during the bond formation is what? So this 1 kilometer per second, that can be written as 1,000 meters per second. Now, if the molecules or if the atoms move at 1,000 meters per second, extremely quick, you can imagine the time it takes to go only 1 angstrom, which is 10 to the negative 10 meters, is going to be a split second, right? So we have an angstrom is 10 to the negative 10. The speed of the atom is 10 to the third meters per second. So if we're going 10 to the negative 10 meters and our speed is 10 to the third meters per second, then the time it takes to go 10 to the negative 10 meters is going to be 10 to the negative 13th. So that's the 10 to the negative 13 seconds is going to be the time scale it takes. Because let's say we were at 1 meter per second. If the molecule was moving at 1 meter per second and we need to cover 10 to the negative 10 meters, then it would take 10 to the negative 10 seconds to cover that. So if we're going 3 times that speed, it'll take, 1,000 times that speed, it'll take 10 to the third more than that. So 10 to the third faster, which would be 10 to the negative 13. Now, I personally did not like this question. The wording was a little bit off, but the question still makes sense. It's really a conceptual unit conversion type of question. Okay, moving on. So what answer could be reported within the correct number of significant figures for the following calculation? And yes, sig figs, there might be a few questions on the exam with sig figs. I know we all hate sig figs, right? But the important thing to know is that we know 2 rules, right? One for addition, subtraction, and the other for multiplication and division. So for addition and subtraction, we want to use the sig figs of the least precise decimal place. So for example, following PEMDAS, right? Following the order of operations. So in following that order of operations, the first thing we would do is these 433 minus 333.9. And we would take this number, whatever the calculator represents, take this number to 1 decimal place. Because for addition and subtraction, we are taking it to the least number of decimal places. So here we have the thousands place. Here we have the tenths place. So the answer to this would be to the tenths place. Now 433 minus 133. So I think this ends up being like 99 point something, but it's to the 1 decimal place. Let me see. My calculator. So 433 minus 99.7.
Yeah.
Thank you. All right. So now we have this 99.7 divided by 2.4. That's in a bracket times 11.9. So Now we continue to follow PEMDAS, and we have division. Now division and multiplication, we're taking the answer to the least number of sig figs total. We're not just looking at the decimal point like we are for addition and subtraction. So we'd have a 3 sig fig number divided by a 2 sig fig number. The answer would be in 2 sig figs, so 99.7 divided by 2.4 is 41.5, which is actually 42 since we're taking it to 2 sig figs. Now we're multiplying that by another number with 3 sig figs, and that would be 42 times 11.9. That's 499. 499.8. So now the answer needs to be in 2 sig figs. So the actual correct answer, it would be 5.0 times 10 to the second, right? Because we want it to be in 2 sig figs. But the answer was 4.9 because it's to 2 sig figs. But it should be 5.0 because of this math. But on the ACS exams, there's not going to be any mistakes like that. Okay, moving on to number 5. All right, now we can get into some real chemistry. So which of the following names is paired incorrectly? It's very important to remember your ions, remember your naming for both ionic, covalent, and for acids. Those are very important things to know for the exam. All right, so we have this one, just looking at the formula, manganese, and then we have a carbonate polyatomic ion. So manganese, carbonate has a 2- charge. And again, know your polyatomic ions as well. So that means manganese will have a 2+. So it would be manganese 2 carbonate. That's correct. Then we would have, this would be xenon difluoride since it is covalent. For naming, a simple trick I like to tell my students is determine if it's ionic or covalent or an acid first. Then you can use the specific naming scheme to figure out what the exact name of it is. Because if you don't know if it's ionic or covalent, you're going to be kind of guessing. And it's important to know. So ionics, you have a metal and a non-metal. Covalence, you have 2 or more non-metals. For acids, you're going to have a hydrogen, 1 or more hydrogens in the front of the molecule. So it's usually H something. This is phosphoric acid. Well, this is not phosphoric acid, but H3PO3, right? You have hydrogens in the front. So that leads us to our answer, actually. The answer is C, because the polyatomic ion, PO3, is actually called phosphite. Now, if you remember the naming scheme for acids, 8 becomes ic, meaning if it was phosphate, it would become phosphoric. But this is phosphite. It would become phosphorus. So phosphorus acid. So phosphite becomes us. So we would have phosphorus acid. That would be this one. So this is incorrect. Then we have dinitrogen trioxide. That's correct. And then we have sodium chlorite. So ClO2 is chlorite. Another thing that's important, remember the 4 chlorate ions. Now I'll write them down. So we have going from the smallest one to the largest one. So the smallest one, so ClO, in terms of small number of oxygens, is hypochlorite. Hypo meaning low, chlorite. So usually the ATE endings have more oxygens than the ITE ending. So we have hypochlorite on the bottom. Then we just have chlorite, ClO2. Then we have chlorate, ClO3. And then we have perchlorate. So per usually means more of. So perchlorate is ClO4. And the easy thing to remember is they all have a -1 charge. Okay, next. Which of the following ions is not isoelectronic, meaning the same number of electrons as neon? So if we go down to the periodic table, we know that once these elements become ions, they attain a noble gas electron configuration. So if sodium loses an electron, for example, it goes back to the configuration of neon. If fluorine gains an electron, like it likes to do, it becomes neon. Oxygen gains 2 electrons, it is isoelectronic with neon. But potassium, if it lost its electron to become K+, it would be isoelectric with argon. So knowing that idea of once an element becomes an ion, what happens to its number of electrons to become a noble gas is important. So the answer for this one would be C, potassium. All right, now number 7. Which of the following statements is true? We have silver as Ag and platinum as Pt. So A, the mass of 10, so off the bat, silver is, if you look at the periodic table, is a lower molar mass than platinum. That means 1 mole of silver is less mass than platinum. So meaning each atom of silver is lighter than platinum. So going into our answers, the mass of 10 silver atoms is equal to the mass of 10 platinum. No, I just said that silver is lighter than platinum, so that's not right. Number of protons in 10 atoms of silver is greater than the number of protons in 10 atoms of platinum. No, because platinum is a higher atomic number, right? This means it is heavier and has more protons. So the protons in 10 atoms of platinum would be more. So that's not correct. C, the molar mass of silver is greater than the molar mass of platinum. No, I just said it. And then D, number of atoms in 110 grams of silver is greater than the atoms in 110 grams of platinum. That is true because silver is lighter than platinum, meaning it will take more atoms to reach 110 grams. Kind of like what the comparison between a pound of feathers versus a pound of bricks, right? How many feathers? It will take more feathers to reach a pound than it does bricks. So same kind of analogy here. Okay, and then E is incorrect. Molar mass of platinum is 107. I think that's just the molar mass of silver. So that's not correct either. Okay, number 8. Determine the number of protons and number of neutrons in platinum 195. So what we need to do, so this 195 represents the mass number of this isotope. So the mass number is equal to the protons plus the neutrons. So we can go down to the periodic table and look for Pt to find the atomic number. And if we look right here, it's 78, right on in the group 8b. So it's 78. And we can say that 195 minus 78 would be 117. So we have 117 neutrons, 78 protons. So the answer would be C. Okay, next, fulminate, which is CNO minus, is a polyatomic ion that forms a bond with with mercury to produce an explosive compound called mercury 2 fulminate. What is the formula of this compound? So with polyatomic ions, we are simply using the name of the polyatomic ion when we're naming it. We don't change the suffix at all. We don't change the ending to IDE or anything like that. And when the formulas of ionic compounds, again, we are taking the charges, and we want the charges of the positive and the negative ions to cancel out. So for Hg2+, we have Hg2+, and then we have CNO minus. So to make these cancel out equal and opposite, we want HgCNO2, because we know that each CNO is -1. We need 2 of them to cancel out with the +2. So the answer would be C. All right, next, number 10. How many electrons does chromium 6+ have? So if it's 6+, this means it is losing electrons, right? If we lose negatives, the charge becomes more positive. Very important concept for all of chemistry. Now, we need to figure out first how many electrons does chromium have to start out with. And we can look at the table, and we can see that the number of protons for chromium is 24. If it is neutral, which we assume here, before it gets the 6+ charge, it has 24 protons, 24 electrons. From these 24 electrons, it loses 6 to become +6. 24 minus 6 is 18. So the answer would be 18, which is D. Next. Balance the following equation and choose the correct set of coefficients. So the way I like to teach balancing is you simply go from left to right and try to balance out each element one at a time. Or if you see an ionic group, such as a polyatomic ion like nitrate, you keep that together. So we have B, so we have 2 B's on the left, one B on the right. So this C, we can make this a 2. I'll put it down there. Then we have bromines. We have 6 bromines on the left, 1 bromine on the right. We can put a 6 right here. Then we have 1 hydrogen on the left, 6 hydrogens on the right. We can make a 6 right here. That leaves 6 nitrates on the left, 3 nitrates on the right times 2, which is 6, and we're good. And then you can go back and check your work again. But you see how easy that is without writing like a chart and canceling things out. For, I would say, 70%, 80% of balancing equations, it's simple. It's simpler to do it this way, and you'll get the right answer on the first try. So it just saves you a lot of time, just going from left to right and going from one element or polyatomic ion at a time, just comparing their left and the right side. So this one would be 1 for A, 6, 2, 6. So that would be D. All right, number 12, which compound below contains covalent and ionic bonds? Now, covalent meaning nonmetals bonding together. Ionic means metal and nonmetal. For A, it's just metals and nonmetals, so that's ionic. Methane is just nonmetals, so that's covalent. Covalent for bromine gas. Now for sodium nitrate, the nitrate polyatomic ion, we know, likes to form a covalent bond, right? That's how it becomes nitrate with the -1. And then it will be bonded to ionically to sodium. So you have covalent bonds and you have ionic bonds. So that's why sodium nitrate would be the answer. Next, which is true about barium chloride. So so what I would say is another tip, general tip, is look at the answers. If it's one of these questions where it's which statement is true, take a brief look at the answers to see what it's asking for or what it's looking for, and then don't look at the answers and look back at the question and see what you can tell about the molecule in question, barium chloride. So I just saw that the answers have to do with charges. So I would look at barium chloride and see, can I find out the charges on my own? Now we know that chlorine is a -1 charge. There's 2 of them. So barium, and even if you didn't know barium, which barium is in group 2A, and it is a 2+ charge, even if you didn't know that and you just knew chlorine, then you can figure out barium from there. So that's all we know. We know barium's 2+, chlorine's 1-. So barium is the cation with 2+, and chlorine is the anion with 1-. So C is correct. That's a pretty easy one. All right, next. If the empirical formula for a compound is C2H3, what is the molecular formula if the molar mass is that? So the empirical formula to molecular formula, basically we're saying the empirical formula is the most simplified version of the molecular formula. So what you do is determine the molar mass of the empirical formula first. So we have C2, which is 12 times 2, which is 24, plus 3 hydrogens. That would make it 27 grams per mole. Now we know that this empirical formula is just the simplified version, and the molecular mass of the molecule itself is 81. Now we can see that 27 goes into 81 3 times. So if we multiply the empirical formula by 3, you get 81. And we can do that with the atoms as well. So C2 will be multiplied by 3, you get C6. And then 3 multiplied by 3, you get 9. So the answer would be C6H9, which is D. All right, now if it's a naming, to name the ionic compound, they already give you a hint saying that it is ionic. And even if you didn't have that hint, you should know by now, because ammonium, NH4, is a polyatomic ion with a +1 charge. And of course, chlorine is -1. So it's ionic. We have to follow the ionic naming scheme. This means no prefixes. Rule of thumb, never use prefixes in naming ionic compounds, ever. So it would be ammonium chloride. That's it. Not monochloride, just ammonium chloride. Good. That's probably the rule I say the most frequently. If you're in my class, you're probably sick of me saying that, but it's true and you shouldn't forget. All right, next. If chlorous acid is written as HClO2, what is the chemical formula for the compound that forms between magnesium and chlorite? Now, chlorite, just like we went over before, all of the chlorites and chlorates have a charge of -1. So ClO2 is -1. Magnesium is in group 2A. so we know it's 2 plus. The only possible ionic formula between them is MgClO2 parenthesis 2 to make the charges of the positive and the negative balance out. So the answer would be C. Yeah. Wait, nope, it would not be C. It would be ClO2 too. So even I got confused. So it'd be D. It's important, read the questions and the answers carefully because these are very similar answers. All right, this is one that a lot of you got stumped with. So a chemical reaction in a solution generates enough heat to increase the temperature from 25 to 52 Celsius. What is the change in Kelvin? Okay. The question is, do we convert to Kelvin before or after? All the time, convert before. So if you convert the temperatures before to Kelvin or to, let's say it was asking for Fahrenheit, convert to Fahrenheit first or whatever you need to convert it to first, then determine the difference, you'll get the right answer. If you do it the opposite, you won't get the right answer. Because if you take the difference of 52 and 25, that's 27. 27 plus 273 is 300. But we know the difference in the heat is not 300 Kelvin. That's a huge difference because it only goes from 25 to 52. And since we also know that each unit of Celsius is the same as each unit of Kelvin, there's no way that makes sense. So the best thing to do for this case is convert each value to Kelvin first, then subtract them, and you get 27. Because the Celsius unit is the same as the Kelvin unit, you can simply just subtract them off the bat and you get 27. But if it was Fahrenheit, that may not be the case, or that won't be the case. You'd have to convert them first and then subtract. So it's important to think about it in the real world because that answer, the answer of 300, which a lot of you put, really wouldn't make sense if you looked at it as, all right, the change in heat from one value to the other. Yeah. Okay, good. All right, now, how many molecules, number 18, how many moles are present in 47 grams of SCl6? All right, so let's find the molar mass first. Whenever I get a question asking about moles and we have grams or we have molecules but we have a compound, I always find the molar mass first, then I look at what it's asking because most of the time you're going to need it. So sulfur is 32.06, and then chlorine is 35.45. There are 6 of them, so we multiply that by 6. And I got my calculator out, 1 second. Plus 35.45 times 6, plus 32.06. That's 244. So the molar mass is 244 grams per mole. Now, how many moles are present in 47 grams? So to go from grams to moles, we just take the grams divided by the molar mass, and we get a fraction of a mole, and that makes sense. And we get 0.19, so that'd be B. With mole calculations, I will say that it's important to have smart calculations. And I've told my class this before, and it really takes the guesswork out of it. Because think about the number that you're given and the number that it's asking for. In this case, we're asking for moles. Moles is a small number, right? It's not going to be 10 to the 23rd moles. It's not going to be 67 moles. It's going to be 1, 0.5, 3 maybe, right? Grams is going to be a larger number. Molecules or atoms is going to be 10 to the 20 something. So just knowing those 3 kind of number ranges alone will help you in what operation you do. So if we're taking taking 47 grams, which is a bigger number, and we want to go to moles, which is a smaller number, we're going to divide. It tells you off the bat, we're going to divide. If it asks for how many molecules we have, in that case, we're going to be multiplying stuff because we're going from a larger or a smaller number in 47 grams to moles, to molecules, which is going to be a 10 to the 23rd number. But in that case, we'd have to do an intermediate because we cannot go directly from grams to molecules. We'd have to find moles in the first place, then we multiply. So again, smart calculations. Always think, does my answer make sense? And just for the record, I know I circled D. The answer is B. All right, next. And this applies not just to simple stuff. It applies to gas laws and everything like that too. All right, number 19. So 30 grams of butane is burned in excess oxygen. 30 grams of butane is burned in excess oxygen. How many moles of oxygen are consumed in the reaction? So again, I'm given a, can you please mute yourself, whoever's muted, whoever's unmuted. Thank you. So we are given a 30 grams of butane, and we're given the formula for butane. First, I would find the moles immediately. Now, C4H10, that is 4 times 12, because 12 is for carbon, which is 48 plus 10 for hydrogens, which is 58 grams per mole. So 58 grams per mole for butane. We have 30 grams of it. So 30 divided by 58 equals 0.517. Okay, that is how many moles. Now, we're being asked for how many moles of oxygen are consumed. So if we know from the balanced combustion, 2 moles of butane reacts with 13 moles of oxygen. Then 0.51 moles of butane produces how much oxygen? So we can multiply this by 13 over 2. So 13 oxygens and then 2 C4H10s. This would be C4H10. The C4H10s cancel out, and we end up with moles of oxygen. So times 13 divided by 2, I end up with 3.36. Okay, number 20. Okay, I'll repeat that one real quick. So for the balanced combustion, we want to look at the molar ratio. We look at the molar ratio between, because it's asking for how many moles of oxygen are consumed. We know that for every 2 moles of butane, 13 moles of oxygen are consumed. First, but we're given a sample. We're given 30 grams of butane. So 30 grams of butane divided by the 58 grams per mole that is butane, that gives us only 0.5 moles. Since we know the ratio is 2 to 13, butane to oxygen, we can then say, all right, if we don't have 2, but instead we have 0.517, we can multiply that by the ratio 13 over 2 to get our 3.36, which would be our moles of oxygen that are actually consumed in this reaction. All right, you got it. Number 20, element Z in the periodic table forms an ion that is +3 with 36 electrons and 89 neutrons. Determine the atomic number. Super easy, because we know the ion is +3. So that means we know the difference in protons and electrons, positives and negatives, is +3 in favor of the protons. So it would be 39 protons, 36 electrons. That's why it's +3. So if we just go down to the periodic table and see what has 39 protons, well, honestly, I don't even need to, because I can just look at the answers and say that 39 is Y, yttrium. Now, we can double check that. 39, yep, it is yttrium. Nice. All right, good. Now, part B, which we require some calculations. So a student begins a chemistry exam with a pencil having a mass of 5.382. The student completes the exam with a pencil and has a final weight, so mass is lost. Assuming the pencil is lead or just carbon, it's not lead, it's graphite, like normal graphite pencils. How many atoms of carbon did the student add to the exam? So I don't like the question. How many atoms? It's confusing wording. How many atoms of carbon did the student add to the exam? A better way of saying it would be how many atoms did the pencil lose? It's the same thing, just the wording could be a little tricky. So it's important to read the question carefully. But anyway, first we want to determine the mass change. So 5.382 minus 5.336. This is the amount of grams that the pencil lost during the exam. And it'd be grams of carbon, remember. So this turns into 0.046 grams of carbon. We take this, we divide it by 12 to figure out the moles of carbon. Moles of carbon would be 0.00383. Then it's asking for how many atoms of carbon. So going from, again, smart calculations, a small number in moles to a large number in atoms, multiplying it by Avogadro's number, which will, again, will be given, and that gives us, let's see, 6.2, 2.30, yeah, this one. So 2.308 times 10 to the 21 atoms. Okay, good. Number 22, how many moles of copper are in 5 grams of copper 1 oxide? Now for this, it requires you to know the charges in the formula of copper 1 oxide. I think some of you got this one wrong because you ended up with the wrong formula. So copper 1 means copper plus 1. You know oxygen is 2 minus. So that means copper 1 oxide is Cu2O, not CuO. That's a common mistake because we want the positives and the negatives to cancel out. So we have Cu2O. So now if we have this, we have 5 grams of it. Now the molar mass of copper, we need to figure out the molar mass of this to figure out how many moles we have. The molar mass of copper is 63.55. So we can multiply that by 2, 63.55 times 2, plus 16 for oxygen, and that equals 143.1 grams per mole. We're being asked for how many moles of copper atoms. That's another thing that's important. So we first need to figure out how many moles of the entire thing. And we can do that by taking our 5 grams, dividing it by our molar mass. Going from grams to moles, it's going to be less, right? Grams is a bigger number. We're dividing by the molar mass to get to a smaller number to see kind of what fraction of a mole this is. If we know 1 mole is 143, then 5 is going to be a lot less than 1 mole, right? Point something moles. So we can do that math, do 5 divided by 143.1, and we get 0.035. But wait, that's not the answer, because this number represents the moles of the copper 1 oxide, not the moles of copper. And look at that. We put that on the answer choices to throw you off. That's not the answer. We would need to multiply this by 2, because for every 1 molecule of copper 1 oxide, we have 2 atoms of copper. I'll say that again. For every 1 molecule of copper 1 oxide, we have 2 atoms of copper. This means for every mole of copper 1 oxide, we actually have 2 moles of copper atoms. So we need to multiply the moles of copper 1 oxide by 2 to figure out the moles of copper atoms, which would be 0.629. Nope, that's wrong. 0.699. I hate that they put answer choices too close together like that, but it would be E. Okay, next, guanidine, which is an important organic base found in DNA. What is the percent mass of nitrogen in guanidine? So first we need to figure out how many nitrogens are in guanidine, and we need to figure out the molar mass of it, and then divide the nitrogen molar mass divided by the total molar mass, and that would be percent by mass. So in this formula, we have 1 nitrogen here, NH2, It's another 2 nitrogens there. So a total of 3 nitrogens. So 3 times nitrogen equals 3 times 14 grams per mole, because each nitrogen is 14 grams per mole. So that's 14 times 3. That's 42. Divided by the total mass, which the total molar mass, which is 42, plus 1 carbon, which is 12, plus how many hydrogens? We have 5 hydrogens, so that's 9 there, 59. So 42 divided by 59 equals 71%, and that is E. That's a nice one. That's an easier calculation question. All right, next. How many grams of potassium dichromate? Sorry, I had like a mental fart. Potassium, and then this is Cr2O7 2 minus. That's the dichromate ion, and a tough polyatomic ion to remember. So potassium dichromate, how many grams of it contains? 8.98 grams of potassium. Okay, there are 2 ways to approach this. So the first thing that I would do, and based on what I kind of taught you guys already, is you take, if you see grams, try to convert it to moles immediately. So I can take my 8.98 grams of potassium, that's a grams, divided by the molar mass of potassium. Now I think that's what, 39 something? Yeah, 39.1 according to the periodic table. So we can divide this by 39.1 grams. 8.98 divided by 31. Oh no, 39. And we get 0.229 moles of potassium. All right, so it's asking how many grams of the potassium dichromate contains that much potassium. So we can say that because the sample has this many moles of potassium, then we know there are 2 moles of potassium, 2 potassiums per 1 molecule, right? So if there's 2 potassiums per every 1 total molecule, since there's K2, we can say that the moles of the total sample is the moles of potassium divided by 2. So take that number, divide it by 2, and we get 0.1148 moles of the potassium dichromate. So K2Cr2O7. Now we're looking for how many grams this is. So now it's pretty easy. We can just take the molar mass of the entire thing, multiply it by the moles to come up with the grams. Now chromate or chromium, so go down to the bottom. So chromium is 52. So we have 52 times 2, which is 104. Plus there are 7 oxygens, so 16 times 7, plus the chromium, which is 104 for 2 of them, plus the 2 potassiums. Each potassium is 39, so that's 78. That's 294 is the molar mass of that. So if you didn't follow what I just said, all I did was I found the molar mass of the potassium dichromate, which is 294. I'm gonna go over this one again after we finish it. So we can multiply this 294 by the total moles that we have, or that we will have, of this potassium chromate, and we get 33.75, which is 33.8. Okay, so to recap that one, there's 2 ways to solve it. The way I did it was, well, let's go over the other way now, and then we'll verbally. The other way to do it is you can find the mass percent of potassium in potassium chromate. To do that, you would simply take the molar mass of potassium, multiply it by 2, divide it by the 294 to get your mass percent. And then what you can do is say, all right, if this 8.98 represents whatever that mass percent is, let's say it's 10%, then, or 20%, then what represents 100%? Then what mass represents 100%? So that's another way you can do it. But the way I did it was I said that, all right, if we have 8.98 grams of potassium, I can simply divide that by the molar mass of potassium. That gives me, in this sample, we know it's 0.229 moles of potassium. If we know the molar ratio of potassium to the entire molecule, which we do, based on the formula, there's 2 potassiums to 1 molecule. So that means the moles of potassium in this sample is going to be double the moles of the actual moles of the actual compound. So we take the moles of potassium, divide it by 2, that gives you the moles of the compound. Multiply the moles of the compound times the molar mass of the compound, and you get the grams of the compound. So that's one way of doing it. But again, there's 2 ways. So then the other way is the mass percent. You find the mass percent of potassium to start out with, and then you say, all right, you make a ratio. You say if the mass percent is 20% potassium, then 8.98 is that 20%. What is 100%? You can simply divide this by that percentage. So both ways are valid. And again, I'm not going to answer questions right now because we're going to go through the whole exam first, but make a note and I will answer, oh, my bad. Make a note and I will answer any question that you have about this question. Okay, so number 25, using the balanced chemical equation below, how much excess reagent is left over at the end of the reaction? Okay, now this one was tough, but it's a good one we should go over. And it really represents the use of the molar ratio. If you have a balanced reaction, you can go back and forth using the molar ratio in the reactants to products, products to reactants. You can use it both ways, and it's an important tool. So here's what I mean. If you have a reaction of 2.5 moles of methane, 4.5 moles of the chlorine, first, if we're looking for how much of the excess reagent is left, we first need to find the limiting reagent and to find out how much of the products are produced. So let's figure that out. If we have 2.5 moles of CH4, this produces, since CH4 is a 1-to-1 ratio with the CCl4, it's 1-to-1, the 2.5 moles of methane, if it were to react completely, would produce 2.5 moles of CCl4. If we have 4.5 moles of chlorine, 4.5 moles of Cl2, the ratio between Cl2 and CCl4 is 4-to-1. So 4.5 of CCl2. Instead of 4-to-1, it's 4.5 to X. So we could take 4.5, divide it by 4, and that gives us 1.125 of CCl4. So basically all we did was we tested each reactant, and we saw how much product does it make. And we picked one of the products arbitrarily. The best thing is to pick the one with the coefficient of 1 if there is one, because it just makes your math less difficult. Okay, so now the limiting reactant is the one that produces the least amount of product, which is the Cl2. Since we have 4.5 moles of Cl2 only creates 1.12 moles of the CCl4, it's limiting. So Cl2 is limiting. Now, because it's limiting, what does this mean? It means that all of the Cl2 is gone. When this reaction occurs, it will react to completion. And you will end up with 1.125 moles of CCl4. That's the goal. That's the end product. The question's asking for how much excess reagent is left. The excess is not the limiting. The excess is CH4. So what this means is that if we use what is produced and go backwards to see, all right, if this is the total, the 2.5 moles of the methane, if that's the total, only some of that was used. To figure out how much that was, we take the 1.125 of the product and go backwards using that ratio to see how much of the CH4 was actually used to make that product. So since they have a simple 1-to-1 ratio going backwards, CCl4 to CH4, we know that to produce the 1.125 of CCl4, it required 1.125 of CH4. Now, we started out with 2.5. So 2.5 minus 1.125 equals whatever that is. Figure that out right now. 1.125, 1.375. So 1.38. So the answer is 1.38. That was a relatively difficult one. So I hope that explanation made sense. So moral of the story is you can use the molar ratio both ways. All right, number 26. The mass spectrometry was used to determine the relative percent abundances of the elements. And so this is relative abundances, so relative percent abundances, meaning these are not percentages, because obviously if they were percentages, they all add up to 100. But these are intensity values. So we're determining the average atomic mass of this isotope or of this element Z, but we have relative abundances. So the way I told my class about it is you view these abundances, these relative percentages, as number of atoms. So if we say we round everything, let's say we have 5, 98, and 100. 5 plus 98 is 103. Plus 100 is 203. You have a total of 203 atoms. Out of these 203 atoms, 5 of them were this isotope. 98 was this isotope, and 100 of them was that isotope. That is what you're averaging to find your average atomic weight. So the math you should be doing is 5.35 divided by the total percentage, which is 5.35 plus 98.51 plus 100, which is 203.86 times that isotope's mass, which is 71.9735. You're adding that to 98.51 divided by the 203.86 times that isotope's mass, 72.9823. And then finally, you're adding to that the 100 divided by 203.86 times that isotope, which is 73.9786. And not sure, I'm not doing that right now, but I think the answer should be around high 73. It should be around here. It should be D. Because you see that most of the abundance is between 73 and 74. Oh, wait, actually, no, it might be, sorry, it might be B. Probably B. Because 73.44, that seems right. Okay, so again, the relative abundances with mass spec, those signals represent intensity and not a percentage. So just keep that in mind. All right, number 27, a drop of gasoline has a mass of 22 milligrams and a density of 754 kilograms per cubic meter. What is the volume in cubic centimeters? So I like to split this apart, and I like to say that, all right, density is 754 kilograms per 1 cubic meter. So we can convert cubic meters to cubic centimeters. So we have the conversion from centimeters to meters. We can cube both sides. So then we have 100,000 cubic centimeters equals 1 cubic meter. From there, we can say that, all right, if the drop of gasoline is 22 milligrams, we can say that this 754 kilograms is equal to 754. Well, it would be 754,000 grams. So 754 million milligrams per 100,000 cubic centimeters. So we're basically saying this is the density. So based on that density, we can say we're looking for the volume. We can say that 22 milligrams times, we can flip this. So we can use density as a conversion factor. We can say that 100,000 cubic centimeters divided by 750 million. I just wrote that in a scientific notation, but too late. Milligrams, the milligrams will cancel out, and you end up with cubic centimeters. So it's simple conversion by using density as the conversion factor. But again, the easiest way to do it is taking the density and breaking it apart. Kilograms, convert that to milligrams, or you can convert the milligrams into kilograms. The 22 milligrams, easily convert that to kilograms. Either way is acceptable. And then the 1 meter cubed, you can convert that into centimeters cubed to make sure your units cancel out. And I think the answer was E. Well, technically it's E and B, but E is the correct number of sig figs, 0.029, because the, actually, no, I think it was B. It was B, because the answer needs to have 3 sig figs. So 22.0 has 3 sig figs, and 754 has 3 sig figs. So the answer would be B. Okay, 3 more. All right, so next, so a 5-gram sample of an organic compound X contains carbon, hydrogen, and sulfur. It was analyzed in a combustion analysis, and you come up with 11.97 grams of carbon dioxide. 2.45 grams of H2O were collected. What is the percent carbon in the compound X? All right, now percent carbon. Now for combustion, we know that I'll just put CXHYSZ as some random organic compound plus oxygen yields H2O plus CO2. The reason why I'm writing this is to show you that combustion is a set equation. It's not going to change. It's always you're adding oxygen and you're creating H2O and CO2. So from this, we can say that the only source of carbon in the products is the CO2. So if we find the amount of carbon in CO2, that is the same amount of carbon from our original organic sample. The same thing goes with hydrogen and water. So the amount of water given can directly tell us the amount of hydrogen in the organic sample. This is not true with oxygen because there are two sources of oxygen from the left side of the equation, right? Or, well, usually there are. If this was instead of sulfur, this was oxygen, it'd be two sources. But the oxygen is usually provided in excess. So we can't determine anything from the oxygen yet. Or in this case, even the sulfur yet. So anyway, with this being said, we know that we have 11.97 grams of CO2. We can divide this by 44, which is the molar mass of CO2, to come up with 0.272 moles. This is the moles of CO2, which also equals the moles of carbon. So because it's a 1-to-1 ratio of carbon to CO2. So now from this moles, we can multiply it by 12. Times 12, we get 3.26 grams of carbon. This is the amount of carbon in the original sample. The original sample is 5 grams. And I know it's a 1-to-1 ratio because CO2 and carbon is 1 carbon to 1 molecule, right? So it would be the ratio between oxygen and the molecule would be 2-to-1. From carbon to the entire molecule would be 1-to-1. So we would take 3.26 divided by the 5 at the original sample, and that gives us 65. I got 65.3, but I think I rounded differently, but it would be 65.4. So that'd be the percent of carbon in the sample. All right, next, we do the exact same thing with hydrogen. So hydrogen, the amount of water is 2.45. So 2.45 grams of H2O, dividing that by the molar mass of 18. Okay, so that question of the part of the question where it says grams of hydrogen and 100 grams of X, basically it's just saying that's another way to think about percentage, is really how many in a 100 gram sample, how much hydrogen or how much carbon you're going to have. But I don't even look at that. We know about mass percent. So that's kind of what it's asking. So 2.45 divided by 18, we get 0.136. This is moles of H2O. So now we're looking for moles of hydrogen. So if we multiply this by 2, we get the moles of hydrogen. Because just unlike carbon and CO2, which had a 1-to-1 ratio, the ratio between hydrogen and water is 2-to-1. Because in every 1 water molecule, there are 2 hydrogens, right? H2O. So we can say that there are double the amount of moles of hydrogen in some amount of water. So now from this, we can multiply it by the molar mass of hydrogen, which is about 1. So we can say we have 0.272 grams. Take this to 0.272 grams, divide it by the total grams of the sample, which is 5, and we get 5.4%. So that would be B. All right, the last part, bring it home. We spent a little bit longer than I'd like to on this exam. I like to talk a lot. That's probably why. But what is the empirical formula of the compound? So taking it home is now that we have the mass percent of carbon, the mass percent of hydrogen, we can simply find the mass percent of sulfur by taking 100 minus those two values. So 100 minus 65.4 minus 5.45, and we get 29. So I'll put sulfur up here, 29.15 grams. And I know it's percent, but I'm putting grams for now because remember, when we first learned how to determine the empirical formula, we've converted the percentages to grams, and then we determined the moles, and then we divided by the least amount of moles to come up with the ratio, right? So the sulfur is 29.15, the hydrogen is 5.45, and the carbon is 65.4. These are all grams. We can convert them to moles. So 29.15 divided by 32.06, that is 0.909 moles. The grams to moles for 5.45 grams of hydrogen is about 5.54 moles. For carbon, 65.4 divided by 12 is, again, so it's 5.45 again. So now we have the moles of each one. I'll put up here moles. We're going to divide by the least amount of moles, which is 0.9. 0.909. That equals 1 sulfur. 5.45 divided by 0.909. That is 5.99, which is very close to 6. So it'd be 6 hydrogens and 6 carbons because that's the same number of moles. They're a 1-to-1. Okay, so the answer would be, what is the empirical formula? It is C6H6S1. So C6H6S1. All right, good. So it's E.